So the next topic is ADPCM. This is adaptive. Just a second, I'm sharing the screen. Sorry, I forgot to share the screen. Can you see the screen now? It's saying that it is getting shared. Kindly check once. It might come. Okay. Okay. So the next topic is ADPCM. So this is adaptive. We already have studied the DPCM. It's a slightly upgraded version of that. Okay. So this is adaptive DPCM, generally called as ADPCM. So let's have a quick review of the DPCM where you used to compress the audio. Okay, and we have seen that DPCM uses what is called as a PCM, right? In its most basic format, we are using the PCM. So let's quickly start with the PCM concept, right? The what we already have studied in PCM is this. So if we use PCM for the compressing technique, right? The very standard rate of uh, the data transfer or whatever the compression happens, right? That is something like 64 kbps. It's a very standard rate that has been is being used in case of a PCM. Okay, but you see, in some of the applications, right, the bandwidth is uh, so it may not be at least this 64 kb also, let us assume. Okay, we may not have the sufficiently large bandwidth which provides you the 64 kbps. All right, because you see the audio data is very less when you compare to the other data which you send along with the audio, or when you save along with the audio, like video. Let's say video is too huge compared to the audio, so I should be able to represent the audio in much lesser space. That is the requirement. Like, so 64 kbps is too much for the amount of information that is present inside the audio signals or the speech, right? So when we don't have the enough space in terms of the bandwidth, right, the speech should be coded at a low rate. Okay, so I'll just write here, this is actually a higher rate, right, for speech, right? So our requirement is that we want to bring this down. Okay, so whenever you don't have sufficient channel bandwidth, or I'll write to save. Okay, to save the bandwidth, right, we need to code the speech at a lower rate. This is what is the requirement, right? At the same time, there should not be any reduction in terms of the quality, right? Or whenever I do the coding, I should be able to come back to my original message. Okay, so this coding is required only for saving purpose. Either you want to save your message. Okay, that's the first thing. And the second thing is that, right, whenever you want to go ahead and you want to transmit this message from one location to other location, then also you will code it and you will send that. But on the other side, I want to go back to the same fidelity which is present in the original speech. Okay, so let's see, right? What all the things we can do? We'll try to look at that once again. This is the fundamental idea behind the ADPCM, right? So my intention is to retain retain the fidelity and quality, right? In the sense, I save it. I want to save the image. Oh, sorry, I want to save the speech in some format. Okay, and when I save, right, you may lose data. No problem. Okay. Anyway, we are not going to listen to that speech directly over there. Whenever you want to listen, you will convert this back to the original format and you will listen. Okay, so during that process, you should be able to show that yes, original fidelity quality of the data is retained. So this is our fundamental idea. Okay, in ADPCM we are trying to do that. So what we do to retain this quality and this, our aim is this. So aim of ADPCM is, right, I'll write 2 points. First, I'll try to remove all the redundancies, right? This is not anyway, even nowadays, whatever the coding techniques we are using, we are not able to remove the redundancies for 100%. Okay, so as much as possible you try to remove, but make sure that, right, you try to remove the highest amount of redundancies, right? Again, in the next part we have to, whatever remains after eliminating the redundancies, we have to assign the sum of the bits in the form of a code to the non-redundant part of the speech, right? In a very efficient manner. So I have to uh, assign bits of our code, okay, to the non-redundant redundant parts. Efficient. So this is what we are looking at whenever we say that, okay, our intention is to study the ADPCM. Now, in ADPCM, the coding of the speech, basically if you see PCM or other methods you use, you go for 64 kbps, right? But in case of ADPCM, this is limited to 32 kbps. You see that there is some standard way of reduction, right? So this happens because of the fact that we have the ADPCM uses two fundamental idea uh, that is called as adaptive quantization and adaptive prediction. We have two things that's what we have studied in a both of them have been studied separately in delta modulation, if you remember, right? That comes under the communication chapter. Okay, so anyway, we are directly taking them from there and we'll try to, right, study the ADPCM. So I'll just write one diagram here which helps you to recall what is it all about. So whenever I talk about the ADPCM, I'm supposed to remember two things first. Okay, it is based on two major what you call steps, right? There are two steps. It's a two-step process. The first step is called as the adaptive quantization. We know that we have quantization, but we are going to use the adaptive quantization, the DPCM, right? If you remember, something like this I had drawn, you split this only for the error required, correct? So something like this, whatever is the error required, you will try to split that. Now in such cases we have fixed this thing, right? The gap between them was fixed, it was not adaptive, correct? But now we try to make it adaptive by using what is called as a adaptive quantization. That's one step, one important step of the ADPCM. Okay, similarly the second step will be it's going to be adaptive. So we had used the several blocks for predicting what is going to come next, right? That's going to be done once again in this case, right? But it will be adaptive, right? So concept is ADPCM. This will have two steps. Okay, perform adaptive quantization. and adaptive prediction. Now, even in the quantization and the prediction, we have two more subdivisions, totally four divisions. Okay, so the first part of the adaptive quantization is called as, it's a forward, it's a forward estimation. Right, so this is in the textbooks, you may find a short form for this, that is adaptive quantization, AQF, which is the forward. Okay, when you have a forward, we know that we can have the reverse also, that is called as a backward. So this is the backward estimation, so normally denoted as AQB in the textbooks. All right, similarly the prediction also has two parts. Okay, so that's again forward, it's estimation, but we'll write it as APF. Okay, similarly you have a backward. All right, backward estimation. So this is written in short form APP. So it's not a very straightforward method. Now it's, we can understand that if you want to achieve the ADPCM representation, right, you have to perform adaptive quantization, prediction. Then inside the quantization, I should perform two steps: forward, reverse estimation, and inside the prediction also I should do the forward and reverse estimation. Actually, we have, for each of them we get one block diagrams. So the idea is that, right, it's not a single step process like the other coding techniques we have used so far, wherein if you have a data directly available in the form of binary or a sequence of letters, we used to solve the problems, right? But that kind of, right, so solving a problem is not possible in case of ADPCM because it is four-step process. All right, so solving takes too much of time, so most of the time the problems under ADPCM is not included. It's a coding problem, like you write a maybe C program or something to solve the whole issue. Okay, so it's like that, it's an algorithm, so we will not look at the programming sorry, we will not look at the problem solving part of this. Right, okay. Now the adaptive, let's look at the two parts: adaptive quantization and the adaptive prediction. So first let's look at the adaptive prediction part. Okay, all right. Now as it says that we are going to predict something. Okay, now uh, since it is a DPCM, we are going to deal with the levels, right? So from the current bit to the next bit, how much change you have, what is the amount of change that you get, right? What is the amount of change that you are going to get from the current symbol to the next symbol, right? This is what you are going to predict, right? So here, the response of a prediction algorithm is something like, it's a forward. So forward means you are going to look at the next, right? Look at the upcoming sample. So what is expected in the prediction part? So you should be able to, or this part, whatever implements this adaptive prediction, right, this should be responsive to the changing levels. All right, changing levels, and also it may be for the spectrum, changing levels and spectrum of the input speech signal. All right, incoming is a speech signal. I just have to be responsive for that. How much level it is going to change, right? compared to the current sample, what will happen with the next sample? This is what I'm supposed to find out. Okay, fine. At the same time, what will be the adaptive quantization? So in case of the adaptive quantization, right, we want to perform the quantization, or we want to use a quantizer that should be capable of operating with a time varying step size. Correct? So it's adaptive, right? We know that whenever I try to sample it out, quantization, you understand, right? At every point in time, I'm able to get a specific discrete value of the signal, right? But that is at a fixed interval of time. But I don't want to do that now. I want to have the step size of the quantizer, right? It's a variable now. It's not a what do you call it's not a fixed value, right? If you remember that we had already studied maybe in communication, mid riser quantizer, mid thread quantizer, something like that. Have you heard of these words? Mid thread quantizer, mid riser quantizer. Those are the two things we studied in delta modulation. Okay, there are various types of what you call quantizers available, out of which I could write, since we already have studied the digital communication part somewhere, right? You should be able to recall that. Okay, so I'll write what is a adaptive quantization means. So this is to use a quantizer which operates with a time varying step size. So the step size should be varying with time. So that means whenever we get different samples and the samples magnitude changes, the step size should also change according to that. Okay, step size, let's try to denote that as delta. So this is the notation, delta of n into ts. So delta we know now. So what is ts? Ts is the sampling duration. Correct. Sampling duration, which is 1 by fs. Correct? Okay, we know that. Now, we need to look slightly in detail about the quantization, because the prediction will be done by a single block, but the quantization happens in various levels. So let's look at this quantization, right? Little bit of detail. Okay, fine. Now, so because of this, what I can do here is that I assume that there is a step size that is delta of nts. Now, this delta of nts is varied. There is a variable quantity coming into picture. If you remember, anything which has to vary according to some other parameter can be considered like a maybe a random variable. Okay, so whenever you have a random variable coming into picture, again I'm taking this concept from the mathematical topic of probability. Okay, so there is a varying quantity with time, so you don't have a fixed way to represent that variation. If at all you see you are able to write an equation for this curve, then that is not a random variable, then that is a variable which can be uh, represented with an equation. But you see, a random variable is not like that. You cannot give a specific equation to that. So in order to get the details of such variable, you have to use the mean, variance, etc. Correct? Are you able to recall that? It's from probability, right? I'm taking that from probability, but I'm going to make a statement which will not include any topic I mentioned. All right, so nothing comes from the probability. I use only the word variance. Okay, so the variation of the step size uh, should it should match one of the parameter of the that variable. It is called as a variance, should match the variance, because it is a random variable. It will definitely follow some PDF, everything we studied in mathematics. So I don't want to go in that much detail over there. I'll just want to bring the word variance here, that is sigma m square, okay, of the input sample. Let's try to denote the input sample. It's a speech, okay, m of nts. So this is the message sample I get at a point, at a point in time, denoted by nts. N can be 1, 2, 3, 4, etc. Right? It shows, it says that it has been sampled already. I have sampled my signal m of t, and I got m of nts. Okay, this m of nts has a variance denoted by sigma m square, right? That sigma m square is the variance of the step size as well, because we are doing this, right? We are trying to write the delta of nts in terms of this. So again, this is coming from mathematics once again. Therefore, the equation that we can try to represent here is the delta of nts, right? The step size variation at any point of time nts should be, right, a function phi. It's not a function, sorry, it's a constant terms, constant times sigma m, sigma m. I'll write a cap here because it is not exactly the sigma m which we considered just now. Okay, sigma m square of nts. I'll tell you what they are. So the sigma m of nts is a estimation, because normally you see, you will never know what is the magnitude with which somebody speaks. I cannot fix that sigma m square as a constant value for a given speech, right? So it, you see, when I talk in maybe when I'm on a call, right? Maybe I using a mobile phone, the volume at which I'm going to talk, right? It depends upon where I am, right? Maybe, right? If I have to be as quiet as possible, means I'll try to keep my tone as low as possible. So you see, you have certain variation, right? During that period of time, whenever I talk, right, it will be, right, very less in terms of the magnitude, right? At the same time, there is too much of noise, I have to talk louder, right? So when that happens, you see the sigma m square is completely different. It's not the same sigma m which I used to talk earlier, correct? Are you understanding? So there is a variation in the sigma m. So what you do, depending upon, you have to make a manual calc. In the sense, you will write a separate part of the code, right? That will estimate, that will make an estimation of what is the sigma m, right, for the current scenario in which we are, right, calculate. We are trying to code this. Okay, so I'll write that part. So sigma m cap, whatever we have written here, right? It is an estimate. Sigma m cap of nts is actually the estimate, okay, is estimated value. Okay, that's why the cap over there. So, right, so it's a sigma estimated value of its standard deviation, because you see, we wrote here as a variance. What is the relationship between standard deviation and variance? If you remember, right, uh, standard deviation is equal to square root of variance. Are you okay? So you see here, we wrote a square term here, but here I'm not writing a square term, right? These terms are not square because I have to take a square root. It is not the variance, but it is the standard deviation. I hope it is clear, right? Okay. Now, again, there is another part coming into picture. The speech, right, data is considered as a non-stationary data, right? It's non-stationary, right? One is, it looks like it's actually a noise signal, right? Basically the speech, I am not able to write an equation for speech, right? Whenever somebody talks, they may say a b c d e f whatever, but you cannot write an equation representing the waveform for a. If I say a, it may look like this. Somebody else may say a, it may follow the pattern, but it's not same. Okay, it depends upon the the characteristics of the organs of each person, uh, which have been used in the production of the speech. Okay, so it completely varies. Because of that, we have to consider this speech signal as a noise, right? There is a whole concept called as a speech processing, right? Maybe you may have it as an elective, if I'm not wrong. Okay, so if you have taken that elective, you will study this a lot. Okay, basically you'll be studying on the same thing, how the speech is represented, and the speech is noise signal, and how do you process the noise. So all terms like this will come into picture: the mean, variance, standard deviation, etc., variance, covariance. By using only those concepts, you try to explore more about the speech. Okay, now, so because of this being a noisy in nature, right, we have to consider this speech as a non-stationary signal. Okay, so when we say uh, I want to implement this particular part, right? The sigma, this whatever is the estimated part is there, right? This is going to change, right? For maybe every 1 second. Let me see, because right now also I'm talking, but you see there is a change continuously. My tone is changing. When I say hello, maybe that's the tone. When I what you are doing, maybe it's a different tone. Correct? So you can relate with that. So that means this sigma cap of NTS needs to be computed, or it needs to be estimated continuously during your maybe it is a compression or during the transmission, or whenever encoding has happened and when you want to come back. Okay, from the encoded part, whenever you want to come back, whenever you want to decode, then also you'll be doing this job continuously throughout. Okay, so that means, right, we have to estimate this continuously. So there are two techniques. Okay, in the actually we are inside the quantization now. Adaptive quantization, right? We have to perform this in two ways now. Okay, so okay, I'll write like this: the standard two methods used for calculating the sigma m cap of NTS continuously. NY. You see here, that means what? Right? I know the answer, right? Already I have written. I'll show you here. So I'm inside this, right? Quantization. There are two methods. One is AQF, one is AQB. That's all, right? We just have to see what they are going to do, right? So the first technique is the AQF. This is in the forward estimation. You are trying to do the quantization in the forward estimation technique. The unquantized sample, unquantized sample of the input speech should be used to derive the forward estimate. That's all. You use the current one to guess your next values. Okay. Similarly, the second technique which we have seen here, that is AQB, correct? It's a backward, adaptive quantization backwards. So use the samples of the quantizer's output to derive the backward estimation. All right. So this sigma cap of MTS is a estimation, right? Maybe I think again in mathematics we have studied this, right? So numerical integration, numerical differentiation, something like that. Have you studied? So have you studied in engineering mathematics? Okay. Some topics such as numerical integration, numerical differentiation, anything like that. It's like you used to solve the problems by using a table, okay, tabular method. We have some values given already, okay, and we try to keep taking the differences and keep filling the these things, right? So as I move to the right, I see that my numbers keeps on reducing. Something like this. Have you studied? Have you done any problem? Possible. Okay, possible. That's again, you see that you are trying to find the differences, right? It's, see, you have two types of differences possible. This number, I'll change the color to represent this number. What I'm writing, it can be a difference of the second number minus first number. Okay, third number minus second number, you fill here. Okay, then the like that. So fourth minus third will be written here. If that is the case, it's a yes. Okay, that's also an example, right? If not that, you can have a reverse or the it's called as a backward difference. You subtract first minus second and fill that. Second minus third, you fill that. Okay, right? This is a backward difference method. You have both types of difference, right? You can take the differences in any of these types. Right. So you see, the first technique says you take the difference in the forward way. Right. So that's what is the forward estimate. In AQB, we do the same thing. Right. Use the unquantized sample of your input, this thing, to do a backward estimation. Right. The samples of the quantizer output. I'll write samples of the quantizer output. Quantizer's output are used to derive the backward estimate. Okay, so that's the fundamental technique we use to do this. Now we'll see the block diagrams of both the techniques. All right, so this is the, so next we are going to look at the block diagram representation of both of them. Okay, so the block diagram of AQF will write first. So it's a forward difference. That's what we are trying to represent here. So let me say that I have the input that is denoted as n of nts, right? It will be directly given to a particular block that is called as a buffer. It's going to hold the data over there for some time. All right. So now our intention is to make an estimation of the levels, various levels that is present. By using the present data, I should be able to, right, guess my next one. So what you do from the buffer, you are going to hold the data in the buffer because of you want to give that data for an estimation purpose. So you have a block called as the level estimator. This is going to estimate the level. And now I have an encoder coming over here, right? So buffers data will be the current data and the estimated data will come from this. Okay. So they will meet up so that the encoder can do the right encoding part of this. So now if you see, this is what is going to be given to the channel, right? In the sense, right, this channel can be the method which you use to save your, or the compressed version whichever you save, right, in the hard disk, right? Maybe it is that, or if it is a communication channel, this can, you are using this encoded output to send it to the other side. Okay, so this is the forward, in the sense the encoder will get both of them as inputs. It's a forward estimation. Now I will show you the reverse part of that. Okay, maybe okay, I have written the shorter diagram, but if you get a slightly different diagram in the textbooks, don't worry, that will be something like this. They will give this to a decoder, Okay, maybe this part is not necessary. Okay, decoder, and the decoder will provide you an output. This is what they are showing, how the decoding will happen. Okay, the decoding also uses another part which comes from the level estimator. There will be a separate level estimator available for the decoder. Okay, maybe this is the part which I don't suggest writing, because anyway our intention is just to see the AQF, that's all. Okay, this is a complete representation. All right. Okay, so anyway, that part which I wrote, which I added now, is not required for a AQF. Similarly, right, similar to this AQF, I will have the other part which is AQB, right? So let's try to represent the AQB. It is the backward estimation, in the sense I will get the inputs like the same M of NTS. Okay, this is given as to the encoder. See the difference? Okay, this is given to the encoder. Now the encoder's output will be given to the that's level estimator. It's not forward. You see, it is reverse. From the output, I will take a part. I'll give it to the estimator. That will give an input to this. So it's a backward. You see, the direction is going backwards. I hope that is clear. Okay, so only that part. Then this itself is a channel, right? And maybe I can write the other part as well. Even in the decoder, we'll be doing the same thing, right? It will be something like whatever comes here, give this to a level estimator. That will provide you an output. Decoder will decode, right, by looking at these two signals. Whatever is received from the channel and whatever is received from the estimator, it will provide you an output according to that. So I'll just write output here. So anyway, even I can write the output. Oh yeah, I already have written it. Okay, fine. So this is what is going to happen, right? This is the simplified block diagram representation of the forward and the backward estimation that is going to happen inside the adaptive quantizer. Okay, so we have a second part. Okay, the second part of our process is called as the adaptive prediction. Okay, so let's quickly discuss about that. In case of uh, the adaptive prediction, speech signals are considered anyway. They already we have considered that they are non-stationary. So there will be a autocorrelation function, and that autocorrelation function, whatever we have, it calculates the autocorrelation function, and it will also calculate the power spectral density. Have you heard the two terms autocorrelation? First thing, what is it? What is autocorrelation? Can you hmm, without considering equation, if you want me to say define or tell what the correlation does, correlation is a method used to find out the similarities. Okay, whether two different signals are similar or not, you can try to identify that by using a process called as correlation. Okay, now you consider two scenarios. I have one signal, original signal, and another signal which is a copy of that signal. Okay, I want to measure whether they are similar or not. Okay, in such case, whatever operation you do, it is still the correlation, but we have a separate name for that called autocorrelation. It's with itself. You are trying to find out, right, is there any similarities between a signal and another copy of the same signal, may be shifted, correct? So first signal is there, second signal is shifted by some amount of time, but the signal still same, right? I should be able to find out, and final result should be yes, they are similar, correct? So that process is called as the autocorrelation. In the other version of the problem will be I have to completely two different signals. Okay, right, one taken today and one more taken maybe few days back, right, collected from some maybe or the best example is radar, right? Radar is doing the other version of the correlation. You send a signal, you keep a copy of that, it hits the target, it comes back, right? It's not the same signal, it's a different signal. You try to perform what is called as cross correlation. One signal is there and the second signal is completely different. Okay, perform cross correlation and get your results. Okay, so these are the two types of correlations possible, which basically trying to find out a similarity. Okay, that's what in case of the adaptive prediction, right? So we have to perform two functions, right? First one, perform the first operation is autocorrelation. So you understand that, trying to find out some similarities. Okay, and the second part is perform the autocorrelation and calculate the PSD, power spectral density of whatever speech input you have. Okay, now quickly going through the PSD, right? It says that power, first term, second term is spectral, and D for density. So spectral density means whenever we hear the word spectral spectrum, that means we are present in the frequency domain. You are not in the time domain. Okay, so this PSD will it may look like this. Okay, this is a PSD, let me assume that this is PSD of some signal. I'll just write the PSD plot. This is a frequency axis, first remember, and it's a spectral density means how much present per something, like, okay, how do you define the density of an object, right? It is the mass per volume, correct, general way. In this much volume I have this much mass, so density is high, right, for metals, because in say 1 meter cube you have more weight. Same thing if you consider the air, less density, because within 1 meter cube you have very less weight, correct? So that's the concept. Now what you are measuring, spectral density of power. Now that means my x-axis is a frequency, right? So like 1 hertz, 2 hertz, 3 hertz, 4 hertz, etc. You see at a particular point 1 hertz, how much power is that, right? 1 hertz contains some amount of power which is more compared to the 5 hertz. That's what is the meaning, right? How much power is present in a specific frequency is what you are trying to represent. That's what is the power spectral density. So we are doing these two operations inside our the adaptive prediction part. Okay, right. So again, I think we have studied this in the digital communication itself, the plot of the PSD, power spectral density, etc. Many things have been studied over there, and also from there we can pick up a point that these operations, right? One is autocorrelation. Again, I think that has been done in the DSP, digital signal processing. Okay, autocorrelation comes over there, and even the cross correlation comes over there. Using that and the PSD part we studied in this communication subject, we from both of them we know that these two functions are time varying functions. Okay, so it in the sense, again, both these operations should be performed continuously. It's not a fixed, I calculate and I keep it. No, that's not going to work, right? You fix your time, like, okay, I take 20 milliseconds. For 20 milliseconds I calculate ACF, I calculate PSD. Next 20 milliseconds repeat that again, because, right, whatever that came earlier is not valid now. My speech data has been changed, correct? So that's why, so perform this thing, okay, perform and calculate the PSD of speech input. I'll add the word continuously you do this. This is going to help you in the prediction. So that prediction can be done in again two ways, right? We already have seen that, right? So the two techniques used are, one is APF, adaptive prediction in the forward direction, right? What do? You have to use the unquantized sample unquantized samples of the input signal should be used to uh, estimate the predictor values. In the sense, predictor's output will be coming by using the unquantized samples. Okay, that is APF. The other option is APB, backward. All right, how the backward happens, we already have seen that, right? The samples of the quantizer output, samples of the quantizer output, and we use another part that is called as a prediction error. Right, both of them are used to derive predictor values. Okay, so I'll try to write the block diagram. So this is the block diagram of AP forward, adaptive predictor forward. So we have the input that is represented as M of NTS, right? So this is given directly to a block which contains two things. One is a buffer, and I'm going to have another part that is the predictor value calculator. This is a block. Right, now this output is given to a summing block where one thing is positive. Its output goes to the quantizer. Right, this output is going to the encoder. So, and we know that the encoder's output will go to the channel. Right, this is the output, encoded output. Now you see there is a part which is called as a predictor. What happens? From this calculated value, we are taking an input to the predictor. Okay, whatever the prediction calculation that's going to happen will come to this. Now from this we have two parts. One, its output will go to this. Okay, and the same thing will be collected and we will be adding them. So this is a negative, so it will be added to this part. So this is a positive, both are positive. Okay, that will be given as input to the predictor. Predictor input are two inputs. All right, so input comes from the output of the quantizer as well as this. So the direction is forward. Okay, so it goes in this direction, right? So that's why you call it as a forward. Okay, it's a forward calculation. Now I'll show you the reverse calculation, right? So the for the reverse calculation, I need to use the APB, right? So I have input that is M of NTS. Now you see here itself I'll add. So from the output I'm taking something and I'm trying to add here. So this is positive. Something comes from the bottom, it is negative. You see this is given to the quantizer. So that's the difference. Quantizer came at last in the previous case, but now you see that it is here itself. This is given to the encoder. All right, so encoder provides you the output, right? But you see here in the quantizer I need a summer block that actually takes the input from the output side and provides you an input. Another input comes from the predictor that is located here. There is a predictor. So whatever that came here, this is one input, and there is another input to the predictor that actually comes from this. So we have the output of the predictor that is going to this, and it comes to this. Okay, and that gives you an input to this. So predictor takes two inputs once again. Okay, so both are coming, one from this side, one from this side. So then it will be fed back as input. Okay, so we have, whenever the ADPCM comes, we have to solve, right, or we have to represent with 4 different steps, right? 4 different steps. Whatever outputs we get, that will be considered as the ADPCM signal.